Hey there, it's section 9.6, and this section's all about dilations. So we've been talking about so far in our, well, we'll get into it. I'll explain that in just a second. So our objective, our goal for today is to understand dilation images of figures. So we're looking with dilations and their images. So what we're going to do first is just kind of go over a couple things that have to do with what we've been talking about. So all of the transformations, let's just read this through. All the transformations you've studied so far in this chapter produce images that are congruent. So those are called congruent transformations. Right there. Other words, they're called rigid motions. They're called isometries. But a dilation is actually a different type of transformation. It is because the size changes. The shape will stay the same, but the size changes. Therefore, it is a similar transformation. Oh, it is a similar transformation. All right? So we're talking about dilations. So basically, a dilation requires a center and a scale factor. So you have to have a center point that you're dilating it from and a scale factor. Usually the letter N represents the scale factor, in case you're wondering. And the value of N totally depends on if you're making it bigger or smaller, so an enlargement or a reduction. So here's kind of a little overview. If the absolute value of N is greater than 1, then the dilation is an enlargement. If the absolute value of N is less than 1, so the third one here, sorry, it's less than 1 but greater than 0, it's a reduction. And if it is exactly 1, then it's congruent. It's just staying the same, so it's not changing it at all. So that's important. So N will never be negative, so that's why it can be negative, but we're talking about the absolute value. So we want to know if the positive value of it, if it would be between, if it'd be greater than 1, less than 1, and greater than 0, or exactly equal to 1. And you'll see that in a second. So a dilation with a center and a scale factor can be written like that. So don't worry about all this stuff right here. This isn't important. Dilations preserve angle measure. The angle measures do not change at all. For any other point, R prime of the. All right. So I'm going to explain this with the picture. So if your shape is PQR and you want to enlarge it by a scale factor of n, and you are enlarging it based on the center. So the center might be inside of it, it might be outside of it. If that's our center, we're multiplying the distance from that center to the point. So like from C to P, or to C to R is right here. C to R prime would be equal to whatever the scale factor is times this. So if we're doing a scale factor of, let's say n is 2. To figure out CR prime, we do 2 times CR. Okay? And that's how you do it on a two-dimensional shape. Same thing, the scale factor works for all the parts. So to figure out, let's say C to P prime would be equal to 2 times CP. And C to Q prime would be equal to 2 times CQ. Now it's interesting that when you multiply it by that, it's farther away from the center. It actually enlarges the figure by 2 times. So then this would also be, it's interesting that this is also 2 times of that. Take this over here, we can kind of estimate. It will be about 2 times of that. Right, and that's our scale factor of 2. You'll see it better on a graph, but we're showing it right now just in 2 dimensions or 3-dimensional space. The figures below show dilations, how dilations can result in a larger figure, and how a smaller figure than the original. So you can go either way, and these are kind of hard to picture, I think, depending on how you're looking at them. But you can go from smaller to larger, or from larger to smaller. If you're doubling it, so the scale factor, let's say the scale factor, where we use n, equals 2, because it's going to be 2 times bigger. Maybe it's 3. I don't know. I'm just estimating. Let's say 3 here. Then if you're going backwards, the scale factor would be The opposite, it's actually going to be the reciprocal, 1/3, because you're shrinking it. It's going to be 1/3 the size. All right. Let's do some examples. Actually, yeah, we'll ignore that for right now. So, dilation notation. It looks like this. It's consistent with the rest of the notation that we're doing, only we're using a D for dilation. The N is the scale factor, like we said there. The C is the center of dilation. So whatever is after that will be what you're dilating about. And most often when we're dealing with a graph, we're going to dilate around the origin. So we'll say O or the for origin. And then again, the figure is at the end. So we got the fancy triangle arrow brackets here. So an example of that would look like this. Example 1. In the dilation of n of about the origin of JKLM. JKLM is an enlargement. Is it an enlargement or a reduction? So if you're going from JKLM, now make note, JKLM is actually the larger one. So if you're going from larger to smaller, you are doing a reduction. What is the scale factor of n? All right, so we got to find the origin. This is where we're the point of origin. So let's just take one coordinate. So let's say you went from, so the origin, so okay, let's say this right here. Okay. Okay is, we can see it 1, 2, 3, 4, 5, 6. Now to reduce it to OK prime, it's down to 1, 2, 3. So that is half the size. So that means, what would you multiply it by? You'd multiply by 1/2 to get from there to there. So our scale factor then, n, would be 1/2. And if it is a reduction, it would be less than 1 but greater than 0. We can check that for other ones as well. Ones that are easy especially we can do right here. We can do OY is 2 and OJ Simpson, or orange juice, which I drink every morning. Anyway, OJ prime was 1, so again, that would be 1/2. And truly, to make sure that it is a similar, it is a true dilation, we'd have to check the scale factor for all of them. So you may have to, and this one you can tell it's just the diagonals. This one you may have to use the distance formula to check. But they are going to be, we're saying it is a dilation, so we're just finding the scale factor, which would be 1/2. All right, let's go on to this next one. What are the coordinates of the vertice of that? So, interesting. What happens if there is no point given? There's no center given. We can assume it's the origin. Okay, I'm allowing you to assume. I know assuming is not a good thing most often, but I'm allowing you to assume if there is no center given, center given, then you can assume it's the origin. So, in order to do about the origin, all you have to do is multiply by the scale factor. All you do is multiply about the scale factor. Take all 3 coordinates, and I'm going to write this somewhere. Whoop. This might be something you want to add. In a coordinate plane, if you are dilating about the origin, meaning if that's the center, then you simply multiply all coordinates by the scale factor. which is great. When it's just about the origin, you just multiply all the coordinates by the scale factor, and that'll actually give you, because all the coordinates, if you have the order pair 2, 1, and you want it to be twice as far away, multiply it by 2, it's going to be 2, or 4, 2. It will be twice as far away. It's just taking the distance away from the origin. So if we have z is negative 2 and 1, p is 2 and negative 1, and g is 0 and negative 2. And we want a scale factor of 1/2. To do that, we multiply all the parts by 1/2. So if our scale factor here, didn't mean to do that, if our scale factor here, oops, is 1/2, we're going to multiply all those parts by 1/2. So we'd end up with z prime being 1/2 of 2, so it'd be negative 1 and 1/2. P prime would be, what's 1/2 of that? So it'd be 1 and negative 1/2. And then g prime, well, 1/2 of 0, so 0, and negative 1. So you can certainly plot it. It's kind of small, but 0, negative 1 is right there. 1, negative 1/2 is right there. Well, not quite. I think my thing is a little off. And negative 1 and 1/2 is right there. Something like that. You can see it's all... No, that looked really bad because my thing is not calibrated correct. But it makes a mini version of half the size of it. All the parts would be half the size. All right? Let's look at number 3 here real quick. The height of a document on your computer screen is 20... So my document on my computer screen is 20.4 centimeters. When you change the zoom setting on your screen from 100% to 25%, the new image of your document is a dilation of the previous image with a scale factor of 0.25. I don't know if you know that, but every time you do that on your computer, you zoom in or zoom out, it's dilating it. Okay, this would be a 0.25 because it's a quarter of the size. So what is the height of the new document? Well, just like we did before, we don't need to worry about what the center of dilation is. Let's just assume that the center of dilation is right in the middle then. So it's still going to be the same thing. You're just multiplying using that same system, and that's going to most often be the case, where 20.4 times 0.25 is going to be your new one. So the new height would be 5.1 centimeters. Much smaller. Alright, so it's going to be still on the screen, but it's going to be a quarter of the size. Something like that. So we'll assume that's 5.1. And everything else would be, again, shrunk by that same scale factor, so it is truly a dilation. Now I do have one problem here. It says triangle ABC has vertices A, B, and C there. Find the image after the dilation centered at origin with a scale factor of -2. Sketch the pre-image of the image. So please do this one on your own before you answer the closing questions, and we will talk about this one in class. This is a good one to discuss. So please have this prepared for next time, as well as the closing questions and the error analysis. If that is all, so think back. Did you learn something new about dilations or understand how to dilate images of figures, or find the dilation images of figures? That is section 9.6 on dilations. We'll see you next time.